Hi-oh, here we are again. Simple machines. Well, what a simple machine simply does is allow you to do work using less force. But there's a trade-off. There's definitely a trade-off. That trade-off is the distance you'll have to move the object. Because if you remember, work is the product of the force and the distance. If you're going to change this, you best change that, because there's no way you're going to change the work. So machines will change the direction of the force, they'll change how much force, but they will not change the work. If we look at this example, this person is lifting a block, and it doesn't matter how they do it. It's the same block, and it has to be lifted the same height, and in doing so, it's the same amount of work. Turns out this guy is going to have the least amount of force, and that's for later in the lecture. So again, I cannot emphasize enough. They do not reduce the work. They simply reduce the effort, how much force you have to pull, but the trade-off is that distance. From this we can talk about the mechanical advantage of something. Mechanical advantage simply talks about how much less force, or how much your force is amplified using some tool. If we look at our formula over here, the force out versus the force in, you want more of this stuff and less of that, right? I don't want to do much. I don't want to put much into it, but I do want to get a lot out of it. And so the bigger the number, the greater the mechanical advantage. This one is ideal mechanical advantage. Remember, work is the product of the force and distance. Mechanical advantage, we're talking about the force. Ideal mechanical advantage is the distance. It's a similar type of relationship, only it's the distance in, how much I have to put in, versus how much out. And efficiency is you're just comparing the two. How much you actually get versus how much you would like to get. So here we have a mechanical advantage of 4. Wow, how far, we're looking at a distance here, but how far would you need to push the lever down in order to lift an object 1 meter? Wow. Well, think about this. We're getting 1 meter out. The mechanical advantage is 4. Now we're talking about distances here. That's how we know this one is what we want to use. So, what do we put in? Yeah, this one's got to be 4. All right. Now realize the force as well. If the mechanical advantage is 4, realize what's going to happen if we had if the distance was huge. Remember, the work is the same, then the force must be small. Very little force in, but a big distance out. So, do the simple machines, do they offer 100% efficiency? No, not a chance. You can't do it. You're always going to lose stuff in the form of heat, friction. There is no such thing as 100% efficiency. But it does turn out, like energy, work is conserved. Remember, work is force times distance. So what you put in is what you get out. The picture shows it very nicely. If I want to get a small force out, I have to move that object a much larger distance than I'm going to get out. And in return, I'll get a much greater force. Let's say my son Aspen, while playing on a teeter-totter, he decides to use it as a lever, smart boy, to lift my daughter. So how much force did Aspen push down on the lever? Well, we know the work in is equal to the work out. The work is force times distance. Well, we're asking if this side is Aspen and this side is Brianna. We're looking for the force Aspen pushed down. What distance did he push down? 2. He has to lift Brianna has to lift up Brianna's weight. So this is 400. And Brianna was lifted 0.8 meters. Now it's just solving for F, and you get 160 newtons. So Aspen used this lever. Did he do more work than simply lifting her straight up off the ground instead of using a lever? No, of course not. It does not change the amount of work, just changes the effort or the force applied. So what was his power output? Well, let's see. Power is work over time. The work required lift was, of course, the force times distance over time. The force lifted was 400, and the distance she was lifted was 0.8, and the time to do it was 4 seconds, and you get 80 watts. So as we look at this, we can talk about all sorts of machines, simple machines. Here we have a ramp. We could lift something straight up to get it to some height. And of course, you'd have to lift the entire weight. But you wouldn't have to take it very far. If we rolled something up an incline, it would certainly be a lot easier. We'd have a much smaller force, but look at the distance. Much, much greater. It's a trade-off. But work is done the same way. If you look at a screw, a nail, big force, but you can go straight on in. The screw you have to twist around and around and around and around and around. Big distance. Pulleys, same type of thing. Notice what happens if we add a second pulley. If we have to lift this mass up 10 centimeters, we have to pull 10 centimeters out of each one of these ropes. In other words, we get 20 centimeters out. But the force is going to be cut in half. With 3 ropes, the force is going to be cut in thirds, but the distance is going to be 3 times greater, and so forth down the line. So finally, suppose a ramp is 3 times longer than the height of the platform. It takes 100 newtons of force to roll, so 100 newtons this way, right? So we got to talk about that distance. What's the weight of the ball? So we're looking for this force over here. We know the ramp is 3 times longer, so it doesn't matter what you say. Maybe it's 1 meter, and then this therefore is 3 meters. So you can do just a comparison, and you should find that the weight of the ball is 3 times more, 300 newtons.